The severity of global warming is intensifying by the day. The impacts of rising global temperatures are increasingly manifesting through various natural disasters. If global warming persists at its current pace, an unprecedented number of people will suffer significant impacts, including water shortages and extreme heat waves. To avoid this climate crisis, it is necessary to achieve net zero carbon dioxide emissions, one of the most impactful greenhouse gases, by approximately 2050. Carbon neutrality has become a global challenge for humanity, and we must pursue its achievement through all available means. One solution is direct air capture, a technology designed to capture carbon dioxide directly from the atmosphere. Capturing carbon dioxide from point sources, such as factories and thermal power plants that emit carbon dioxide in a concentrated manner, is insufficient to reduce greenhouse gas emissions. DAC technology is essential for collecting CO2 that has already been released into the atmosphere. However, DAC faces various challenges in its practical implementation, making innovation urgently required to address them. Let us introduce Cryo-DAC, a new DAC technology that we are developing. The key characteristic of Cryo-DAC is its utilization of cold energy derived from liquefied natural gas. LNG, used as fuel for thermal power plants and as a raw material for city gas, is imported from overseas in liquid form at -160 degrees Celsius. We are working on improving the energy efficiency of the DAC process by utilizing the cold energy, which absorbs heat from the surrounding air, from LNG as it evaporates, and then leveraging the phenomenon in which cold energy causes CO2 to turn into dry ice. At first, the process of Cryo-DAC involves sending air into the absorption tower, where it encounters the absorbent liquid, allowing carbon dioxide in the air to be captured. At this stage, instead of the conventional method of regenerating the CO2-rich liquid through heating, the process uses a sublimation chamber, a heat exchanger installed downstream of the regeneration tower, where CO2 is cooled and solidified using the cold energy from LNG. This process reduces the pressure in the regeneration tower. As a result, CO2 can dissipate from the CO2-rich liquid without the need to heat the liquid. The collected dry ice can be converted by rewarming it in the sealed sublimation chamber and fluidizing it as high-pressure or liquid CO2. To store or utilize the captured CO2, a compression process is required. However, Cryo-DAC can produce high-pressure CO2 directly without the need for compression. Cryo-DAC seeks to substantially reduce costs, which poses the most significant challenge for DACs, by capitalizing on its advantages, the capability to operate at ambient temperature, and the elimination of the need for compressing the captured CO2. The energy and cost efficiency of Cryo-DAC is assessed through an analysis technique called process simulation. Results show that Cryo-DAC can achieve significant energy savings compared to the DAC heat regeneration method used in the conventional chemical absorption process. Additionally, it has been determined that Cryo-DAC can operate with significantly lower energy consumption compared to other existing DAC systems and has the potential to be fully competitive in terms of recovery costs, including equipment expenses. Cryo-DAC is expected to utilize low-grade waste heat or ambient heat, as the temperature required for regenerating the absorbent liquid is lower compared to other systems, and it is characterized by the ability to operate at ambient temperature. Japan is a pioneer in the use of LNG, with an import volume reaching 70 million tons annuity. The CO2 collected with this technology is liquefied and transported by ship to countries with abundant renewable energy, where it can produce methane by reacting with hydrogen. The methane produced in this method is called e-methane. Our goal is to utilize e-methane as a fuel source by liquefying it at low temperatures, transporting it back to Japan, and then using its cold energy for CO2 collection. The demand for LNG, a low-carbon fuel, is anticipated to experience sustained growth in the medium term during the transition phase toward a decarbonized society. Furthermore, The utilization of liquid hydrogen's cold energy can also be explored once its production and distribution commence in the future. Currently, efforts are underway to commercialize Cryo-DAC through collaborations with universities specializing in material development, process design, sensing technology, and economics, as well as with gas companies, engineering firms constructing chemical plants, and chemical manufacturers.
The raw material for city gas, liquefied natural gas, LNG, contains ultra-cold energy at -160 degrees Celsius. In this project, we refer to this as LNG cold energy. This LNG cold energy is utilized to freeze carbon dioxide gas into dry ice, creating a vacuum environment without the need for a vacuum pump, which is a key feature.
Being involved in the development of the Cryo-DAC process, I have come to appreciate both the innovative efficiency of this process and the challenges it presents. We aim to develop the highly innovative and multifaceted Cryo-DAC process into a fully fledged industrial solution by fostering collaboration among industry, government, and academia, ensuring it goes beyond just a technological achievement. By capturing carbon dioxide at an industrial level, we believe it will finally be possible to enrich the global environment for future generations and the world they will inhabit.
If we continue to do nothing, global warming will only accelerate further. If we do nothing, global warming will continue to worsen. Therefore, we believe that advancing the development of technologies like Cryo-DAC and other carbon-neutral solutions can contribute to addressing global warming.
In the future, it is expected that synthetic methane, or e-methane, which is produced from hydrogen derived from renewable energy and captured CO2, will be used as a fuel. This e-methane is also expected to be liquefied and distributed in the same way as natural gas. In addition, technology for transporting liquefied hydrogen is also being developed. The temperature of liquefied hydrogen is even lower than that of liquefied natural gas, at -250 degrees Celsius. If a world where e-methane and liquefied hydrogen are widely distributed becomes a reality, it might be possible to obtain the necessary cold energy for Cryo-DAC without relying on fossil resources. We will continue to address each technical challenge step by step and work toward practical implementation.
The research on CO2 capture utilizing cold energy commenced as a dissertation topic in a laboratory at Nagoya University. Initially, only a select group of individuals, including students, were engaged in this research. However, with the collaboration of numerous colleagues, the research and development have progressed to the extent that the operational readiness of the Cryo-DAC bench plant is imminent. By steadily addressing and solving each technical challenge, we are advancing toward our goal of contributing to carbon neutrality through Cryo-DAC.